Today we are going to start the analysis part. We have already talked about the modeling, and which means once you have created the model, the next step is to run the model to get some results and then do the design. And we will divide this analysis into two parts. One is for gravity loads and one is for wind and earthquake and lateral loads. Alright. So gravity loads, you might think this is just easy or simple, but you will find that there are some complications that arise from gravity load analysis. The purpose of the gravity load resisting system is basically to transfer the gravity loads applied at one location to the foundations. So we need the whole system. If I'm standing here, my load should be transferred from this location from the slab to the beam, beam to the column, column to the foundation, and so on. So this whole path which follows to transfer the gravity loads is what we need to study. And direct path systems or indirect path systems, slabs supported on walls which directly supported on foundations, or slabs supported on column and columns directly supported on foundations, or indirect vertical path in which slabs supported on beams, beams supported on column, other beams, and beams supported on column, and so on. So depending on how long the path is, the analysis becomes equally complex. So we are going to study both the paths, say direct and indirect, or multi-path. We have talked about the systems, flat slab, flat plate, beam slab, beam dash slab, reference slab, and now we come to the big question which I told you I will answer later: beam dash slab and beam comma slab. And then you asked me at that time what's the difference between beam slab, beam hyphen slab, and beam comma slab, right? So now we will see that difference and see why we call them like this. And then girder, comma beam, so these are with commas and this is with a dash. Okay? And we will see why they are called like this. So let's first of all talk about how people have been taught and people have learned, or people think. And as usual, right from the first course, every time when we know what you think, turns out to be wrong, right? So we will do the same thing here. This is what people think, that when you apply a load here, you can draw these lines and you can assume that this load goes there, this load goes there, this load goes there, and this load goes there. That is how traditionally everybody has thought about load transfer, and that's how you calculate the load from the slab to the beam, trapezoidal load or triangular load. And if you open any book, that's what they will tell you. But we will find that this is not really the case, or this may not be the case. In this particular case, if the green lines represent walls, and all of the walls are directly supported by foundations, and there is no slab on the side, this may be true in that case only, right? But this is a rare case. You will almost never have these cases in all buildings. Second one is another extreme case where you only have columns, 4 columns, same slab supported on 4 columns. Then traditional thinking is that all of this load goes to this column, this load goes to that column, this load goes to that column, and this load goes to that column. That's how we think. I don't know what happens to the load which is right in the center. It's quite a confused load, right? Which column to go to. And right at this point, right? Or right at this line. But traditionally, we calculate the loads transfers to be like this. Actually, the load transfer will depend upon many things, right? But net load transfer, we can assume to be like that. So these are two extreme cases: that loads going directly to walls as uniform load, or load going directly to point supports as sum of the total load in that tributary area. We call it tributary area. This concept is called tributary area concept. Now we have a problem. Suppose edges are not walls, but rather beams, right? And beams are supported on columns. Now tell me how the load will be transferred. Will this load go here and here, or if this is a load here, what will that load do? Will it go this way and here as the green line, or will it go directly to that column from here? This is not an easy question because it will depend on the relative stiffness of the slab and the beam, and that's how the loads will finally be transferred. So the bottom line from this is that load is not transferred based on geometry, load is transferred based on stiffness. And that is what many people do not realize or do not take into account. They transfer the load based on the geometry, whereas the load will be transferred based on the stiffness, not geometry. Right? So that is the point that we will try to make more and more as we go along. Now things become even more interesting. Suppose this is the same room and I put a beam in between. Now traditionally, if you just put a beam there, traditionally you will do like this. You will divide this slab into two parts, right? Then you will say this is slab 1, this is slab 2. Then you will say this load will go to that beam, this load will go to that beam, and then you will design this beam to carry the load to the wall. Am I right? That's what you will do. But again, my question is, what if the beam is equal to the thickness of the slab or a little bit more than the thickness of the slab? Can it actually take that all load and transfer? Because the slab next to that is just the same stiffness of the beam. So this beam actually, just because you draw a line does not mean there is a beam or there is a support there. It will become a support when it becomes very stiff, infinitely stiff, equal to the stiffness of the wall. Only then this thing can be assumed. Anything less than that, the beam will not take the load as you imagine. It will take some load, but not the same load as a wall will take. Because wall is infinitely stiff, beam is not. So beam will also deflect. So this load transfer mechanism actually will not work. In reality, this does not work. We need to consider the stiffness in this transfer. More complex issue. You have a wall on one side, you have three beams on this one, and you also have in between secondary beams. Now there is a load here. What is that load going to do? Go this way, that way, or a load is here, what is it going to do? So now you absolutely cannot determine, you cannot even determine which one is main beam and which one is secondary beam if the span is square. Right? So you cannot know which beam is supporting which beam. And where is the load transfer? You absolutely cannot judge what the load transfer path is, because it's not up to you, it's up to the system to determine how the load will be transferred. You cannot tell the system in this case do this way. It will depend on the relative stiffness of many things, slab, this beam, that wall, this beam, everything. Which means that we conclude that the load transfer in gravity systems, and another one, three-step. You have this beam, this one, that one, right? So you can see from here that as soon as you keep adding more and more elements, the load transfer path starts to become more and more unpredictable and more dependent on stiffness, just like determinate and indeterminate system. The determinate systems are geometry based, indeterminate systems are stiffness based. So this is the same situation. These systems are highly indeterminate, so the load transfer mechanism will depend on the stiffnesses of the components rather than the geometry that you see. Just because you draw a beam does not mean it will become a beam. It will become a beam when it will have stiffness. and how much stiffness it has will determine how much load it will carry. Right? So that is the bottom line, and that is what brings us to the definitions of different systems again. Now, if you transfer a load, you apply a load directly to a point, that means here, at this point, it can go directly, so you do not need any calculation. Load and reaction are equal, simple. Second is that you have a load which is transferred to a line object and supports. So here you can calculate by hand based on the distance from the point of the supports. You know, this load is equal to this distance divided by this total distance multiplied by the load, and opposite, right? So based on that, you can calculate the loads directly. Correct? Then, when you have system like that, which is an area object or a 2D object, when you apply the load here, now things become more complicated because the stiffness of this system, stiffness of the columns and other things will be making it more difficult for you to determine where the load is going to go. Because if there are some subsystems in there, this is not something that you can, this is not possible, this is not possible. Right? This also will depend upon if there is a connection between them, then hand calculations may not be possible anymore. Because the two columns may have different stiffness. So the load going to them will not be equal even though the distance is equal. So even if you put the load in the middle, if this column is bigger than that, this side bending moment will be more and reaction will be more than that side. So that means even the reaction will be based on the column stiffness and not only on the geometry. So stiffness is the key in determining the load transfer mechanism. And if you apply a load to a solid, to a volume, then it's very difficult how the load will go because it will create, it does not even follow the traditional, depending upon the stiffness and so on, it will depend upon how much, like we say, the solid could be water, so you don't know how the load is going. It just may go on the sides completely rather than going down, right? So it's a soil. You apply the load to the soil like this, it goes sideways, right? So depending upon the properties of the solid, the load may go vertical, horizontal, or even upwards. You apply a load, it may actually go upward and called upheaving. So it all depends on many things. So for volumes, the predictable response is very, very difficult, how the load will, where it will go. So this is simple. Area load going to line load if the walls there 2 points. So if you have 4 points, the load has no other way but to go to 4 points because there is no indeterminacy in this case. There is no stiffness. There is stiffness if this column is bigger, more load will go there. But let's assume that they are in this case of the same size or the connection is not rigid. And when you do that, then you have all kinds of unknown things happening, dotted lines. So the load can go any way depending upon the relative stiffness of beams and columns and slab. So it may go like this if this is very thick, or it may go like this if it is very small. It is all dotted now. That means we don't know. We have to determine it, right? And that is the key lesson from today, is that the load is transferred. This is now details about the load transfer for some of the typical cases. And this is now the question is, now comes the interesting question. Choice of the elements that we talked about the other day. If you used plate element here, plate has a bending stiffness, so the load transfer element, the load transfer will be determined based on the stiffness because plate has a bending stiffness, so it can transfer the load. But suppose you used membrane, load cannot be transferred through membrane, it will just fall down because membrane has no bending stiffness. But Again, to make the structures economical in terms of the running time, programs like ETABS and other programs allowed you to have rigid diaphragm and membrane in the floor, because when you mesh it by plate, too many elements takes too long to run when people don't have any patience. So they use membrane. When you use membrane, the load transfer through stiffness cannot work. Then the geometric load transfer, the program sort of falls back on the geometric load transfer mechanism. So if you use for a slab, for example, a membrane, and then you apply the load on it, the program will fall back on the old concept of the geometric load transfer because it has no stiffness information anymore, right? We try not to use that any now, but previously we had no choice, or we had little choice. So this is something that is based on the geometric load transfer that the programs will use. I do not recommend it that you use that. I recommend, or we recommend these days, to mesh the floor using shell or plate elements, in fact shell elements, because you also need in-plane diaphragm action, right? So this is just many cases of load transfer based on geometry, that if you don't have stiffness, what will happen to the load? Where will it go? Conceptually. For example, if you had only two walls and no walls here, then load will go here, this load will go here. Of course, this is not a stable structure. This corner will go down, right? It's a cantilever. But suppose you had, somehow you managed it, load will go this way. It doesn't mean that the structure is stable. It just means where the load will go to the supporting system. Not talking about the design of the slab itself, rather the load transfer. So these are some cases where you can see how the geometric load transfer would work if there was no stiffness assigned to the floor. Useful information for understanding the load, and also useful information for hand calculation of support loads. Based on the area, you can quickly calculate where the load is going from each slab, and you can estimate the load on the column. For preliminary design, before doing the analysis, because you need the column size for doing the analysis. So to determine that, you can quickly draw this one, but you should be able to do hand calculation for geometry-based load transfer based on it. This is called a tributary area concept, right? Still useful in many ways, but not useful for the design of this gravity system. Useful enough for the loads on the support system within reasonable accuracy. Now we try to see how the deformations will work on the surface load transfer. So this is a slab which is supported by 4 columns, and then if you apply the load, it will be formed like this. And these contours tell you the moment values in that location. And different views of the surface load transfer, and that is what you can do for that. For different kinds of, you can plot deformations, moments, and different kinds of moments from the analysis. Basically, what you need to see is that we have to mesh that slab into plate or shell, not membrane, right? So remember that for gravity load transfer, you need to do at least plate. We do shell because we also sometimes have in-plane forces. Now comes a little bit more interesting problem, interesting look at. This is a slab. We meshed it by plate elements. Then we put 2 beams in between, one big beam, one small beam. And then we put 2 equal big beams, and we put equal small beams. So I'm just going to show you how the stiffness based load transfer will work, and how the bending moments and deformations will be affected by that. So in this case, first case, you get this dish type of a deformation, right? So the slab bends like this. It's a two-way action. you get here there is a positive, negative moment, and you get this dish type of it. This is a two-way behavior. Depending upon the aspect ratio, this shape will be different. So it's quite clear, it's simple. Now you put small beams. Interestingly, the small beams did not change the dish behavior. That means these beams just deflected with the slab. Just because you put the beams there, it meant nothing because they were small. So they did not alter the behavior of the slab. The slab still acted as if it was a two-way slab, and the beams also bent with the slab because they were just not strong enough, right? And so if you try to design these beams based on a geometry base, you will kill them. You will transfer so much load to them which they cannot carry, and you will put a lot of reinforcement which is totally not going to work, and you will dangerously design this as 3 panels whereas it is acting as 1 panel. And this is something that I have seen a lot engineers making this mistake, and then cracks appearing at the bottom of the slab because they think there's going to be a negative moment here, but actually the moment is positive. So they stop the reinforcement bottom and you get these cracks under the beam that they cannot understand why there's a crack under the beam, because there was a positive moment present there, but they thought the moment will be negative because they used the beam as a support. Now you can see if one beam is bigger than the other, the cup shifts this way. So this becomes actually one square panel. This becomes more like a support. So there is going to be negative moment here and positive here. So now the relative size of the beam will make all the difference in the behavior. And if the two beams are big, then you can see that it divides into 3 panels, almost, right? So that means big beams, small beams, and the relative stiffness is very important. But the question is, how big the beam will be before this happens? Wait for it. So you can see the load transfer here is like that. Here is still like that. Here is 3 panels, and here is still like that. So here it divides into 2 panels, one big and one small, right? Here it divides into 3 panels, and here it does not divide into any panels, conceptually. So you can see that even though the same span of the beams, depending upon the size of the beam, the load transfer and the panel divisions will be totally different, right? Not what you will think by looking at this slab layout. So the geometry-based transfer here is completely incorrect, unless the beams are very big. Okay. Now let's see how big they need to be before this happens. Now we go to another slab system. We say this is a 5-meter slab, and this is a slab, and then let's study what will happen if we change the beam size and see how the load transfer will work here. And this is very important study. This is what will happen if the beam is 300 millimeter. Slab is 200, beam is 300. So you can see the beams is bending with the slab as if it doesn't even exist. As you can see, it's just going like this. And you have negative moment on the support, and here you have positive moment. So this is bending as if this is one strip, one strip, one strip. Right? Beams are not doing anything. This is almost going, there's no negative moment here over the beam, no red color. So if the beam is 300 millimeter for a 5-meter span, it is not going to act like a support. Beam is 500. Actually, 500 millimeter beam for a 5-meter span, normally people will not even allow you to make it. It's really too much, right? But even if when you make it, then you can see a little bit negative moment coming up and some differentiation coming up, but still the beams are deflecting quite a lot together with the slab. So they are still not acting as a support that you would expect them to act. Beam 1 meter deep for a span of 5 meters. If you do that, you will be fired immediately, because no one will allow you 1 meter deep beam for 5 meter span, right? But if you do that, yes, now you have supports and you have negative moment and now you have the cups. So that means unless the beams are extremely stiff, almost like walls, they will not act like a support. And they will not, the geometry based load transfer only works when the beams are really, really stiff. At least 5 times stiffer than the slab they are supporting. Right? So from this, you can see if I move the beams, slab will have deformation in moments like that and like that. And this is, you can see the transition, reversal. Negative moment over the column to negative moment over the beams. And transition gradually going from this way and this way. This will never happen because you are never ever going to have beams which are going to be 1 meter deep for a span of 5 meters. Impossible, right? Which means that in reality, beams do not act as a support for a slab system. What they do is they deform together with the slab and they share part of the load. How much? Depends on their stiffness. And this is something that was recognized by ACI code in 1977 when they changed the design method for slab system from coefficient based method, which was the original old way, to this stiffness based method in 1977. So they recognized, but before that everybody thought beams are supports. And British, especially the BS code, continued to do that until 83. So they followed behind another 5 years before they changed their approach also in this context. But now we know this to be a fact that this is not the case. And moment in beams you can see also changing, and then when you go to this level, only then you get real positive moment and negative moment in the beams, right? Like the way it should be. Here you don't get much positive moment in the beam because they're not really supports. So this gives you an idea how the relative stiffness of the systems change the distribution of load carried by the slab and the beams, and from the top you can also see it's like this. Now this leads us directly to the ACI method for design of slab systems. They have a single method for design of all kinds of slabs. They do not make any distinction between wrapper slab, brick slab, joist, beam slab, and so on. Only distinction is beam comma slab. So all systems which is beam dash slab means where the beam and slab act together to carry the load, we call them beam dash slab. And beam comma slab is when the beams and slab are different and the slab is supported on beam. So this is the beam comma slab, this is the beam dash slab, Now you understand. So when the beams are not stiff enough and they deform with the slab, we call it beam slab. And if the beam is strong enough to act as support for the slab, we call it beam and slab or beam comma slab. Simplified analysis and design of beams. If beams were to act as beams, you can calculate the bending moments from that using the simplified coefficients developed by the codes. Interesting observation here. So you can use this concept of simplified analysis and design for one-way slabs. That means slabs which are clearly supported on beams or walls. So you can take a strip of that slab and you design them as a beam of 1 meter width or half meter, whatever width, right? So you can use the one-way slabs can be designed in this way when they are supported on beams or walls. So it's very simple. This is the definition. If your slab is falling within this definition, you can use this simplified method. And basically step 1, simple continuous beam, estimate thickness based on deflection, analyze using coefficients or software, compute reinforcement at critical sections, check thickness for shear. So these are the steps. I don't want to repeat them. You must read them. Very simple step to design one-way slabs, right? By hand or by computer. Thickness calculation. These are the simple rules. You can estimate the thickness based on the span. If it is not continuous, L by 20. If it is one side continuous, L by 24. Both sides continuous, L by 28. Cantilever, L by 10. What's wrong with these equations? These are the equations taken from the code. As usual, code is wrong. Why? What's missing? Load. It doesn't care about the load. It is giving you the same depth of the beam whether I have very heavy loads or very small loads. So this deflection, this height estimation has no indication of the load level. I may be carrying very light loads, I may be carrying very heavy loads. So people may be misguided in using these calculations when they do not consider the loading. So this is important to understand that this is based on a typical loading in a building, average normal loading, nothing heavy, right? Moment coefficients. This is how you calculate bending moment at the various location. First span, WL squared by 11, WL squared by 10, 11, 10 and 11 both, 16, 11, 16 and so on. This is how you can easily estimate the bending moment at various points along the beam. Now the interesting thing is that if you compare, you do the same beam in SAP or ETABS and you calculate the bending moment, you will find them to be very different from this one. And then you will say, what happened here? The code told me that I can use WL squared by 10 or 11 here and WL squared by 16 here, but I am getting moments which are very different from this one. What happened? Why would the code give you wrong formulas for bending moment of a simple beam? And in that case, whom should you believe? The code or ETABS? The problem is like this. ETABS is going to give you the results based on the stiffnesses and everything that you provide, based on the elastic stiffness, assuming uncracked section, and for that one load pattern that you are considering, UDF. But in reality, there are many cases to be considered that you should consider. Alternate load, alternate span. For example, only load here, no load here. So that will increase the moment here. Only load on these, not on this one, will increase the moment in here. So there is going to be an enveloping of the bending moment diagrams because of the alternate live load patterns that you did not consider in ETABS, which should be considered according to the DS and other codes. So you must consider alternate live load patterns, many of them, 5 or 6 of them, before you can come up with the moment diagram, and you must consider the bias of the two. So you basically get moment envelopes. What is a moment envelope? These are load patterns that you need to consider. All spans loaded, adjacent spans empty, adjacent spans loaded, and only this span loaded and adjacent spans empty, right? Like load. Just for example, you have class here, low class in the next room, both rooms having classes, right? That kind of scenario, live load patterns need to be considered. So obviously for each one of them, the moment diagram will be different. For this one, the moment diagram will be like that. For this one, the moment diagram will be like that. And for this one, moment diagram will be like that. And for this one, moment diagram will be. Each one of them will give you a different moment diagram, different moment value in the same span. And you should get the envelope for each span, the maximum of each of those negative and positive loads. So if you take the envelopes of all of those loadings, you will find that you come close to this for a typical load pattern, right? So these, many of the formulas in the codes are based on more work than you normally do. So it's based on several load patterns, and they take the envelope and then convert them into coefficients. So it's an easy, if you don't want to use this, you must use full analysis with all the load patterns, and only then your results can be reliable. So sometimes the codes give you shortcuts, which should be, you must know the rules and you should follow the rules. That's what they say, but you should also know when to break them, right? The problem is that we sometimes don't understand the rules and we break them, or we don't understand when we follow them. Both ways it's wrong. Following the rules without understanding is dangerous, and breaking the rules without understanding is even more dangerous, right? So we should understand how these things work and what their background is. Two-way slabs. Two-way slabs supported on big beams or balls. Big beams means stiffness of the beam is greater than 5 times stiffness of the slab. Right? In that case, we can use this approach. Step 1, step 2, step 3 is almost the same step. We have many ways to do the direct analysis method, moment coefficient method, strip method. We used to study that a lot when we were in class because we needed to study them. There was no other way. Now there is another way, finite element analysis, that you can use. You don't need them, and they don't teach them anymore. But yield line theory, moment coefficient, strip method, we used to study so many things because we had to do hand calculations for two-way slab design, right? And then VS Code and other people came with the coefficients, yield line theory, finite element method. So there are many methods that you can use. Obviously, these days we just use this for everything, right? But sometimes you need to do simpler design, and two methods still people use in offices quite a bit. One is the coefficient method for two-way slabs, and one is the equivalent frame method or direct design method for flat slabs. You need to understand those because those are the hand calculations still. You cannot always use software because unless you use Pyrotic, because those software are very expensive which can do this analysis. $8,000, $7,000. So if you cannot afford that, we still need to use these methods, right? In any case, we should understand them. So two-way slabs, thickness calculation. This is a little bit more complicated than thickness for a one-way slab where we just divide the span by some factor. Because now we have two spans, two-way slab. So we need to consider the ratio between long span and short span, which is beta, and we need to consider the steel strength. Interesting question now. What is steel strength doing in thickness calculations? Let me put this question another way by looking at the question. If you use high strength steel, will your slab thickness be smaller or larger? If you're using high strength steel for the same loading, will you get more reinforcement or less reinforcement? Less reinforcement. When you get less reinforcement, then the composite effect of the steel will be less or more. Right? So then you need to compensate that with a thicker slab because you are using less steel. So the high strength steel, if you use, the reinforcement will be reduced and the effect of the reinforcement will be less. You need to increase the thickness to compensate because the modulus of plasticity of the steel is the same. So if you are using low strength steel, you will require more reinforcement which has higher stiffness, so you can reduce the thickness. Got it or not yet? Okay. That's why this formula is there. And this can be quite substantive because the difference between high strength and low strength steel is 1.5, 40 grade, 60 grade, 50% more. So the amount of reinforcement can be substantially different. And when you multiply the amount of reinforcement by the modular ratio, which is 10, the effect on the moment of inertia is quite large, especially of a cracked slab, where the concrete is already gone. So most of the stiffness of a cracked slab comes from the steel stiffness. And steel stiffness depends on the elastic modulus multiplied by amount of steel. And amount of steel will be higher for low strength steel than high strength steel. That's why this whole thing is there. You can take the perimeter of the slab for estimation purpose and then divide it by a factor between 180 to 120. That depends on what we are going to tell you now next. And the factor depends on the continuity cases. If it is like this, you can use a larger factor. If it is like this, you need a smaller factor. So 120 here, 180 over there, and in between you can choose approximately. So that is a simpler formula which is based on the perimeter of the slab, which is actually converted from all those things into simplified approach, right? But it's a very, very rough formula to estimate. And these cases are very important because they will govern your bending moment and everything. So 9 continuity cases look like this. 1, 2, 9. So we need 6 bending moments in a two-way slab and 6 reinforcements to be calculated. Positive short direction reinforcement and positive short direction moment. Negative short direction moment and negative short direction reinforcement. Negative discontinuous support. Even if this side may not have any continuity, there is still a little bit of negative reinforcement we provide because of just even the slab is supported by wall, has some kind of a rotational stiffness there and a wall on top of that, so we still provide some continuity reinforcement, discontinuity reinforcement there, which is typically 1/2 of this one is provided on this side, right? Just to make sure that there are no cracks there. Long side, same thing, 1, 2, and 3. So basically, when you design slabs, two-way slabs like this one, you need 6 reinforcement quantities to be calculated. 3 in each direction, right? So 6 moments, 6 steel bars, and that's why it takes a while. Next one, maybe we do it next.